So now I think we will continue with the presentation of Markus on the work conducted for detecting transparent objects. If it's fine with you, Markus, I give you now the control so that you should be able to share your screen. We see your screen and full screen. Perfect.
Okay, thanks for the introduction, Anthony and Charlie. My name is Markus Vincze from the Technical University in Vienna. We worked on recognizing these transparent objects, which are everywhere, not only in the lab domain, but also in related domains. I mean, at home we have classes a lot. My group is called Vision for Robotics at TU Wien. We try to make robots see and do everything with objects. So modeling and tracking of objects, recognition and classification. And of course, we want to know something about the function and the affordances of objects so we can manipulate them. And I will now dive into the methods that we developed, but start basically with something that is like state of the art with non-transparent objects, so that just you see what's going on in the world and how we extended this. So this is just one method we developed and published recently. And the big movement that there was in the last years was moving from real images for learning, which is nice, to synthetic images for learning. And in this code paper, we could show that basically you can get the same, if not better performance, if you only learn from synthetically generated images. So you use nice graphics engines to render images, you have the object models available, and you just create scenes. And we could show that this is not only possible at all, but it's also fast. So here you see an example with a stack of many objects. On the right side, for example, you see the images with up to 90 objects. And we can do that basically 25 times in a second. So it's very good to know that if the learning is done right, you can learn novel objects from basically using a CAD model and just doing it. As an example to do that, we had a recycling project where the idea was to find all the screws, find the type of the screw, and then use a robot to unscrew it. So that's an amplifier of huge antennas, many years old, hundreds of screws, so that's only the top layer, but if you remove that, there are even more. And we did exactly that. We learned, we knew what type of heads these screws have. We modeled them. You see this on the left side here. And then you learn this by making sure that the system, this network, learns only the object and not the background. So what you do is basically you put these objects in front of the arbitrary background. An example is on the right side. It's really arbitrary, so we take just like some random image data sets for background. You see that the screws are then in random colors, also to make sure that whatever they look like, they are taken, but we know exactly what is the feature what we're looking for because we put them into this image. And this is very successful. You saw an example here for finding the screws. The problem for the robot is then that the screw is very small. So the pose, the position and orientation is not really pointing upwards, but it's like a bit tilted in any of the directions because the screw is so small. So in this example, we use the depth image to find the surface, the plane basically, and use the plane to get the surface normal and the direction for unscrewing. And that's a combined approach. You use the best of whatever modality you have. And kind of using this experience, we extended now our knowledge towards transparent objects. What is the challenge for transparent objects? Unlike other objects that have texture and are opaque, the depth image is pretty much useless. So you have this on the bottom an example scene, and from the top you see from the side. So from the from my viewer, the viewer would now be on very much on the left. You see from the side into the image, you see that the image, the green plane, is reasonably well represented in the data, but all the other stuff is like there's spare data points. Some data is actually completely missing because of the transparency and so on. So we need to find actually the data in the color image again. So we cannot use the depth data directly as we did with other approaches, but we really need to go back to the color image. So what we did here is generate the data set and made sure that we have really good ground truth. That's the first step I will explain. Then modeled actually transparency, so how the optical ray goes through a transparent object, and use this to create hypotheses for the object, not only recognizing it, but also for the pose estimation. So how is it located and oriented in space? And then we asked ourselves, you know, is that sufficient? And as you heard already, we really want to have a confirmation for this project if the objects are in the right pose. So we needed this verification step. And I will also explain how we do that. And finally, of course, this was integrated in the robotic system, and you saw already several videos, so I will not show them again. One of the big steps in the beginning is ground truth. So if you devise a new method, you need not only data. I mean, yes, we can create synthetic data, and I will show how this is done in this example, but we also need to evaluate the method. So we need real data, and the real data need ground truth, because we need a real assessment on how the method works in reality. So a typical example is shown here. This is actually from a data set someone else created. And the problem is that, yeah, it looks superb on this color image, but the problem is from the side, the depth is basically very, very difficult to assess. I mean, although the outline is perfect, we see that from the side, there's a bit more than a centimeter of deviation. And that would be a real problem for grasping. I mean, beyond 3 or 10 millimeters, you know, it's really getting not very accurate, and we might have problems. So we need already a method to make sure that the ground truth is better than what is there, and it should be not only working for these textured objects, but also for like transparent or shiny objects. So what we came up with is a robot cell. You see the KUKA arm moving around the cell, and actually we take 104 images of the cell at different heights and locations and all around the scene. You see a bit that there is a pattern for registration, and we can put objects there. They can be transparent or not transparent. We can have a CAD model, or in this case, we actually spray painted one of these transparent canisters, which is gray, and then use the photoneo laser to get an accurate model just from several of the images. And with this, we can arrange the scene shown at the top left. We just take like 3 views. We put the object model there. We make sure that it fits into the scene. This can be now done one time for every object. And the nice thing is, if you do it for one view with the assistance of maybe an orthogonal view, you transfer that object pose in all the 100 and other views in the data set. So it's relatively cheap to create a lot of ground truth. The model actually we use is a NERF model, which stands for neural radiance field. It's a volume model, so we have really the complete model of the object done, which is then very helpful for grasping, because the volume is important to place the object in the scene, which also is completely volumetric. And here are a few more sample scenes. You see that we have mixed transparent and not transparent objects in this TraceBot data set. So now comes the important step, the recognition of these objects. As we heard already, we have transparent objects not only in lab automation, but everywhere in the environment. So that is really an interesting thing for robotics. Whenever we do tidy up at home, it would be really cool to have classes grasped and not only the textured objects. So in TraceBot, we have a few different objects. You see here the canisters and the bottles. I will later present specific methods for fill level and the tubes. They are a bit different. Tubes are deformable, and the fill level is a very specific thing in a bottle. So we devised specific methods for that. But again, it's coping with the transparency. So the first step we did for transparent objects is we explicitly modeled this transparency using what we call the mating renderer. So basically, we used the graphics engine to render the attenuation and the flow on how light passes through transparent objects. These renderers or that you have at the moment available, we use Blender, are very, very good, and they also provide a mask. And these are the three things that we use in our full data set. So for every of the annotated things, one thing is shown on the right here, and several more I showed before. The first step, because from there we can learn a neural network for the detection. And again, we used only synthetic training data, and then evaluated and TraceBot and actually on other data sets against state-of-the-art method. And we could show that our method is actually quite better than those other methods. So how does this work now in detail? So the attenuation is the greater flux, loss of the flux intensity through a transparent object. And the refractive flow is basically the distortion because of whatever curvature or geometry the object has. So we learn these from the ground truth, use them in the detector, learn in encoder and decoder, and then basically find these specific masks, find features, and in a patch PNP approach, match the features to the model, and from this estimate the object pose. The learning again is similar to what I showed you before. So there is the target object. In this case, we used actually the target objects we had from other data sets because they were available. That was the TOT and the Trans32K data sets. You see the objects here, and again we used arbitrary background. In this case, we just used random samples from the COCO data set, which has millions of images, so it's wonderful to learn quasi the object versus the background. You see nicely how this rendering creates the distortion and attenuation through the object for all these examples. And you see that the domain is actually quite different, but it picks up how transparent objects are modeled or how actually are seen in a real environment. And this is then used for our detections. There are some examples. Again, you see that the images are relatively, the objects are relatively small in the image. On the very left side, you hardly see them. And then you see so that you better see what's going on. I show you quite some other examples where, again, on the left side is the original image, and on the right side is an enlargement of the object detected and the environment around it, so that you really see. I mean, on the left side, even the human eye has difficulties to find the glasses or the marks, and on the right side, you very nicely see that the bounding box perfectly displays the pose, so the position and orientation of the object. So as we all know, this is wonderful, and we achieved with nearly 94% very nice scores. But we all know that these learned methods may fail or even have hallucinations. So what do we do then? So what is if the pose estimate is wrong? I mean, are we grasping into the object? Are we damaging something? So this adds this verification step, or Charly put it, which we developed in this TraceBot project. And the answer is yes, you want just to have one more step using the hypothesis that we created and just verify if the hypothesis makes sense. And making sense means there must be an overlay between the model that I have now, the pose, and what I actually see. So going back from the model and reprojecting inverse rendering into the image if the outlines like coincide. But we can also use physics knowledge. Objects need to stand still on a plane surface, which we have in all the examples here. And already quite some experience with that. I show you here an example from an older paper. Work started already nearly a decade ago, where we had more complex kitchen scenes, but with textured objects. We created in the center many hypotheses, and on the right side, basically the objects in front are all detected correctly with the best possible pose and no intersection, for example, between the objects. For texture, that was good, but how can we extend that to transparent objects? So one possible thing is the inverse rendering, so the silhouette. The second possibility is the geometry. So we know the planar surface. The object needs to be stand stably on there. And finally, there's yet another thing we can have. Once the object is grasped, we can use actually the tactile sensing in the gripper. And Mathieu is talking in the next section about that, to also improve the pose estimate that we have. So we put that all into one system. Here is shown on the right side. You see now how it moves. That's from the silhouette. Once the silhouette is settled, we use the plane coordinates. I mean, there's a huge plane visible below the object, so we can use that. We know the Z direction, and then we can basically adjust the X and Y coordinates so that the object stands stably. The nice thing is that can be done at any location. As long as there is some plane on the bottom. First, you align the silhouette with the inverse rendering process, and then you use physical plausibility to get the pose right. Something similar is done, but different for the gripper. In the gripper, we don't have the planar surfaces, but we have the tactile points where the robot grasps the object and touches the object. And Mathieu will tell you what signal we have from the tactiles, but basically we know exactly where on the finger we grasp the object. And we have this feedback with the gripper opening, so we have a location too. And we can use that to get rid of the object so that the initial hypothesis shown on the left side is corrected to what is most likely more correct on the right side. You see that it's not perfect yet, but it's definitely much better than before. And with this, we have a very good estimate where the object is within the gripper, and then we can place it exactly where we want to place the object. I said there's like two specific procedures that we also developed, which are necessary for the domain. So one question always was asked is, I mean, one of the reasons why they are transparent objects is that in several reasons you want to know the fill level of the objects. For this, we came up with a specific procedure. First, we detect the object. So in this scene on the right side, we detected two objects, the bigger object, the bigger bottle in front, and then that small slice of the smaller bottle in the back side. Here we see that the bottles are marked with a red and green star. So this is basically using the model knowledge and how the object is oriented in the world. We can see where there's the top of the bottle and where's the bottom of the bottle. And then we trigger basically or prompt SAM, which is a segment anything method for Meta AI, to segment quasi the water or the liquid in the bottom and with the green star, and the top of the bottle with the red star, and give us basically what the segmentation believes is the fill level. And then using fill level and the edges and corners of that, we fit an ellipse, because typically we know the bottles are round. So what we see visually is an ellipse, and we can fit an ellipse from the edges. And this is a geometric constraint that helps us very much to get much more accurate data than without doing this fitting process. There's one more step actually we can do is, we know that the plane of the ellipse should be parallel to the surface plane, because gravity is obviously looking downward. unless the table is tilted, which would be a weird setting. And that also helps us to very accurately get this fill level plane. Finally, we have developed a specific method for tubes. In this case, around plastic elements connecting all these bottles, needles, and so on. And they need specific treatment because they're deformable. So the method is you cannot learn a specific CAD model, but we rather need to learn a local property. And we combine this with classical vision methods like edge detection and plane extraction. Plane extraction we always do because the support plane is always a very good indication of where we are. And we use the edges to train a detector for tubes that are local segments. And then we basically add these segments. They cannot have two sharp bands. They can, of course, be occluded, as you see in the example below. But you see that we nicely actually get the tubes and the tube location. A bit more tricky is actually the depth estimation here, because you see that this tube is actually a double tube, which makes it a bit tricky to get the depth. So whenever it's lying on the table, it's clear. Whenever it's deviating from the table, it's a bit less unclear. I mean, yes, it needs to be above the table. It might go to the needle, for example. So then the needle pose actually gives an estimate of the tube. But there's still some open work to estimate the tubes in whatever location they are. Finally, we have extended that work for a special request we had also coming from the pharmaceutical domain, which is plastic bags. So there are so many plastic bags and everything is wrapped in the sterile environment, so that we just tested how we can do. And actually you see in the top left the original image, and then from 3 different views the same images, and you see that we get very nice segmentations, not only of the plastic but also quite a lot of the objects that are inside. Of course, only sometimes, not all the time, or the labels. Here you see that sometimes we get the vials, but sometimes not. That just depends on the specific view. But it's already very, very good initial start to handling also plastic bags. Finally, in the project K4 together with the University of Bremen, we did that for drugstores, detecting all the objects, and also there many are wrapped in plastic, and you see that we can detect them also nicely. Finally, we want to tidy up at home. So this is in our lab with our robot. That's actually the Toyota human support robot, with the idea to have a robot at home that does tidy up. And you see that on the table, the robot is grasping all the objects. So the first one he could take from the front. The second one he could not take from the front because of the orange. So he took it from the top. There's just some grasp reasoning, and this one again is grasped from the side. You see already that the mobile robot and the arm is much less accurate than the arms, the universal robot's arms we had in TraceBot. With this, I come to the conclusion. We developed what is called Reflow 6D, a model of transparency for learning the flow and attenuation patterns, so that we can learn from synthetic data how to grasp, how to detect, recognize, and pose estimate objects for manipulation. We have real data for ground truth and then serious evaluation in a real-world environment. The nice thing is that comes back to a question that was asked before. How do we now have like a different kind or a completely novel object? And the nice thing is, since we learn from synthetic data only, we could basically relearn the method from synthetic data with a novel object, which is relatively fast, adds a bit, and makes it much easier to cope with novel objects. If the novel objects are relatively close to objects we know already, we might try one of our zero-shot approaches. So that's an approach that learns basic features and then just adds the model without even relearning. Because the features are so similar that what the network learned might be reused. We could show that that method is very successful for glass plastic and can be extended to tube specs and even the film level. And the poses are accurate enough, so you do reliable object grasping, particularly since we have this verification step that really makes sure that what we see is what is really in the image, and whenever there is an object hypothesis wrong, we can cope with that. Thank you, and I'm open for questions.
Thank you, Markus. Yeah, for me, it was really amazing to be part of this project and see how you develop different answers to than all the others before, because always in the past when I asked somebody to recognize the pose of a transparent object, the single answer was difficult. And yes, you answered also it's difficult, but you found together with the team of the whole project, you found answers to detect the pose and verify the pose. Any questions regarding the vision? I do my best to unmute you if you raise your hand, or just write it into the chat if you have a question.
Maybe in the meantime, just to complete the question we had before about what happens if we have similar object of different size. Do you know what? So you mentioned that we could use a similar object. I mean, we could update the object model without having to relearn the complete system. So, but typically,
Yes.
how would you? If we have, I don't know, different bottles of different size, a single learning could be sufficient. How complex it is to adjust the
single learning could be sufficient, because what we are using is the plane the object stands off to get the distance.
Okay.
Basically, you get with the neural network, you get basically the view where the object must be, and using the plane from the depth estimation, you get basically, okay, here it needs to stand, so it must be this size.
Mm-hmm.
So you can exploit that. Of course, that gets tricky if objects don't stand on planar surfaces or are stacked. But even there, it will stand on another object. We are using this that objects can't intersect; they need to be separate. I showed an example for the textured objects where this is done, and the same is done here.
All right, thank you. Any other question?
And yeah, thanks, Charlie, for adding this. It's a real pity at the review, this wonderful example where a reviewer wanted to have a different background, and we had quite reflective carton, kind of a bit shiny carton prospects of TraceBot, and all the detections worked nicely, and nobody made a picture or video. I'm so disappointed, because it worked so nicely, the system, and the pose estimates were actually really very good, and the robot could grasp it. But yeah, luckily it worked.